I'm going to be going over a couple of homework problems similar to what's in 16.3. I'm going to be looking particularly at 38 and 42. 41 I've highlighted here because it's another similar problem that has a worked out solution accessible to you in Wiley Plus. So I would encourage you to try that one and check it on your own. Tomorrow, April 21st, 2020, at our 8:30 Zoom session after you've had the morning from 8 to 8:30 to practice, we will be going over some other homework problems as well as practice problems from 16.3. The ones that I would suggest are 43, 45, 51, and 53, all odds where you can see the answers and some of them at the solutions as well. And if you want to give yourself a challenge, look at 52. And those 5 ones I will do by request tomorrow during that Zoom meeting, as well as looking at more 16.5 and 16.3 problems. All right, let's jump right into 38. So numbers 38 and 42 that I've picked highlight the 2 different applications of the triple integral that we'll be looking at. So this one is where I integrate an actual density function, and that by integrating the density function over a volume, my answer will be the actual mass. So in this case, they're giving me density in kilograms per cubic meter, and I'm going to integrate over this solid region whose volume is in cubic meters. The solid region they're describing to me with a system of algebraic inequalities, so it's up to me to visualize what's going on. I have a trough, which is where animals come to drink from, and it has triangular cross sections, and it lies along the x-axis. So that's what I've sketched here briefly. X goes from 0 to 10, and the slanted sides are given by these equations: z equals y and z equals negative y, and z is stuck between 0 and 1. So I've drawn this cross section in the YZ plane, what this should look like in the YZ plane. So if I go back into 3 dimensions, that's going to be planes coming up from the x-axis at these angles with the slope of 1 on either side. Something that I notice here, my density function is only dependent on x. The trough itself is symmetrical with respect to the x-axis. Furthermore, the actual function is also going to be symmetrical. The function only depends on x, and if y, right, here's my y-axis, if y is positive or y is negative, the x values will be exactly the same, changing from 0 to 10. So the density of the sludge, the food inside this trough, is the same on both sides of the x-axis. That can make my integration a little bit easier because I'm going to integrate just this red half and then multiply by 2, because I have symmetry not only of the volume, but of the actual function as well. This is going to make it a little bit easier because now if I look at my y's, I'm going here from y equals 0 would be this plane, standing right up here, the xz plane, until I get to just this side, which is the positive side, right? This is the side where y equals positive z. And then I can just double that answer because I know that the density on this side is the same and the volume is the same. So that's going to be my approach. So because of that, I am actually going to start with the y's instead of the z's. You can also start with the z's, then you'd be going from this plane, right, where z equals positive y, up until where z equals 1. So if you want to try it that way to verify you get the same answer, that's fine. Right? The mass is unique. There's one specific mass for the finite amount of sludge in this trough. However I compute it, I should get the same answer. I'm going to do it starting with the y's just to show us that we can. So I'm going to go, and y's, you always start from the smaller to the bigger. So I'm starting from where y is 0, and I'm ending here where y is equal to z. Then I would next integrate the z's, and the z's I know go from 0 to 1. And then I would end with the x's, which go from 0 to 10. So setting up that integral, I already put down that we observe the symmetry. So setting up the integral, what that is going to look like is, I said inside, we're saying the y's go from 0 to that plane where y equals z. Whoops, hopefully. And then, so that's going to be my dy. Then I was going to integrate with respect to z. So my z's go from 0 to 1. That was given. And then I can integrate with respect to x, and the x's go from 0 to 10. That was given. And since I want to actually find the final mass, I'm integrating the density function, e to the negative 3x, which was also given. So now I can do this one step at a time, and ultimately when I get this answer, let's not forget, I am going to multiply it by 2. That's why I'm going here from 0 to z, because I'm doing half the trough, which has density that is going to be symmetrical. The density values will be the same on the other side, which would go from negative z to 0. So instead of going from negative z to z and having a much more complicated integrand, I'm going to go from 0 to z and then double it. Again, if you didn't see the symmetry, you certainly could still do it and get the same answer. If you observe these things, however, it makes your life easier. In this case, we'll actually do the integration for practice. So now remember, I'm treating this as a constant. I'm integrating first with respect to y. So I'm going to get y e to the negative 3x. I'm going to evaluate that between 0 to z. And then I still have to integrate with respect to z and with respect to x. The z bounds are 0 to 1 still. The x bounds are still 0 to 10. So now I'm substituting z in place of the y because I had integrated with respect to y. So that gives me inside z e to the negative 3x. And then I am still going to have to integrate with respect to z with respect to x. Bounds between 0 and 1, 0 and 10. And just so that we're discussing, when I plug in 0 for y, 0 times anything is 0. So that would be minus 0. So I won't write that down. Now I can go ahead and integrate with respect to z. So e to the negative 3x is still going to be treated as a constant. Let me just move this down further. It's still going to be treated as a constant. And I'm integrating with respect to z. So the antiderivative of z would be z squared over 2. And then I'm multiplying that by e to the negative 3x because I'm treating that as a constant, evaluating the z's between 0 and 1. Then I will have to integrate that answer for x's between 0 and 10. So in that case, let me keep moving. Here's our next problem for you to be excited about. So then we now need to plug in the 0 and 1. So when I plug in the 0 and 1, when I plug in 1 again for the z's, and let's not forget, sorry, I kind of got sloppy here. We're going to take this final answer, of course, and multiply it by 2. So this is still up at this step 2 times that whole answer, 2 times this whole answer. And as I'm moving down here, I'm still going to have to multiply this final answer by 2. So now when I plug in the 1, I'm going to get 1/2 e to the negative 3x times 2. So the 1/2 and the 2 will cancel out. So that's going to leave me with just e to the negative 3x minus, now I'm plugging in the 0 for z, so that gives me 0. And now I'm going to integrate this thing between 0 and 10 dx. Here, this is a review of Calc 1. You would actually need to use a u substitution. I'm going to let you guys check that on your own. It's a pretty simple one. So when you do the u sub here, you should end up with e to the negative 3x over negative 3 between 0 and 10. Here's what we've been talking about all along with the zeros. Notice I don't have the multiply by 2 because I already took care of that there, right? That's why that constant of 1/2 got reduced because 2 times 1/2 is 1. So I have already done the multiply by 2. So now when I plug in 10, I get e to the negative 30 over 3 minus, and when I plug in 0, I get 1, over negative 3. And if I want to make that look a little bit prettier, it's already a common denominator, so that would be e to the negative 30 minus 1 all over negative 3. And if I don't like the negative in the denominator, I can multiply the top and the bottom by negative 1. That's just a final beautification step. And then that would become 1 minus e to the negative 30 over positive 3. And this, my units would be in kilograms. And if they asked for an exact answer, I would leave it like that. If they wanted an approximation, I would put it into my calculator. The second problem that we are going to do is going to be number 42, and this one we'll go ahead and set up. Let me move this down here so we have some more room. This one, they're just asking us to find the volume between these two planes. So this is a much simpler problem But again, the setup is the hardest part. So the first thing is realizing I have two ways to find volume. One way I can find volume is to look at the volume under a surface, basically above the xy plane. The second way is I can take the triple integral of just dv, where my bounds of integration describe the solid that I want the volume of. Generally speaking, when my volume is stuck in between two surfaces, the triple integral is going to actually be easier to set up because I can describe my z's, the bottom and top of my surface, as my bounds of integration. Otherwise, if you use a double integral, you actually have to subtract. Because if I just integrated, for example, the volume under this plane above this region on the xy plane, now I have to subtract out or add to the extra volume under the other surface. So in this way, I'm going to choose to use a triple integral. And I'm going to realize that using the idea that the integral over that solid, if I integrate just dv, is going to give me the volume of that solid. So the whole problem really reduces to how do I describe this solid as a system of three algebraic inequalities in space. I'm going to start with z, right? I generally start with z unless, like in the first problem, I see some strong reason that makes it seem easier to start in another way. So when I look at the z's, I have these two planes, and I can describe them both in terms of z. So we've got z solving for z equals 6 minus 3x minus 4y. And the other one is z equals 6 minus 2x minus 2y. They were pretty nice to us with some user-friendly numbers. If you need to go onto Wolfram Alpha or other graphing software and look at these, you can decide. But my main goal is to figure out which one is below and which one is above. I can see they both start at 6 if x was 0, 0. And then as I move away from the origin, as x and y get bigger, since this is times 3 times 4, and this one's both of them only times 2, I'm subtracting bigger and bigger numbers here, right? So this one is actually going to get smaller and smaller. So this one is going to be below. This one has bigger outputs of z. So below my surface is, going to be some plane here. That would be the 6 minus 3x minus 4y, because those have lower outputs. And then above, also starting from 6, is going to be some plane over here. That would be 6 minus 3x minus 4y. And what I am trying to find is the volume in between these two things. Planes go on forever. I'm not going on forever. In between those two things and above, let's draw another quick cross section. Above the line, right? If I look here just at the xy plane, I want to be above this triangle where here's my line x plus y equals 1, and they wanted the area less than 1 where both x and y are above 0. So here I am above this triangle in between those two planes. That's the volume I want. So setting up our integral, which is all we're going to do here is the setup, I am going to start with z, which I find generally the easiest. I'm going from that plane on the bottom, the one that has the smaller z value, so 6 minus 3x minus 4y, and I'm ending on the plane on the top, 6 minus 2x minus 2y. I'm just integrating the differential, the dv, that's what makes my answer volume. So the constant 1, I'm starting with z. I'm going to integrate next with respect to y and then with x, although you could do dx and then dy would be the same thing. So now I need to describe y in terms of x. So if I look here at my xy plane, y starts at 0 when y is equal to 0 on the x-axis, and y ends when I hit this line. So y is starting at 0 on the x-axis and ending in that line. If I were to solve that for y, and I see I have a type, well, that should be x plus y, that would be y is equal to 1 minus x, right? So to kind of emphasize, these are my bounds for y. Then lastly, I can integrate with respect to x, so then x is going to go from 0 to 1. So that triple integral is going to give me the volume of that solid E, which again is this wacky volume in between these two planes above that triangle. I encourage you to do some more practice or pause these and try